All right, so here we go. I'll mute you guys just so you guys are good to go. All right, so this is a table for you guys to know some integrals. There's a total of 20 different integrals, and these are all, they're indefinites, but if you notice these indefinites that we have here, there's no plus c, so don't forget that the constant should be there. It's just they've omitted it. They said that they omitted it. It's probably for printing purposes, but these are these 20. I did post these notes up for you guys today. I don't know if you saw that. But these are them. And I want you to use these as a reference, okay, as you go forward. Know how to do them when showing work, but also be able to reference them when you're going to do some problems in terms of speed, right? If you're just trying to get things done, you can use these references to do it, but make sure you know how to do them by showing the steps. Because maybe I'll give you one of these and be like, all right, this is the answer. Now prove it to me by demonstrating the work. Does that make sense? Okay. All right, so let's go into our first example. And what's cool about these problems now is we've all gotten so used to, all right, there's one answer in mathematics. I love that there's one answer in mathematics. You know, you're right or wrong. Well, in calculus, we start finding out that things are much more complicated than we thought. And so I'm going to show you 2 ways to do this problem. And the answers are not going to look the same, but they're both correct. Okay? So the first way I'm going to attack this problem is I'm going to break this up into the integral of tangent cubed x secant cubed x dx, right? Because 1 over cosine is secant, right? And so then from here, from some of the rules that we learned earlier in this chapter, we know that I can break this up to become tangent squared x secant squared x, and then get secant x tangent x dx, correct? And then to attack this problem, what do we do? What would you do?
Would you use U substitution?
It would be a U sub. What would you want to use as your U sub?
Secant squared?
Close.
Just secant, right?
Just secant. Because if you use just secant, the derivative of just secant would handle this piece here for us. So that means that that tangent needs to be changed in terms of secant. So I would go, okay, secant squared x minus 1 times secant squared x secant x tangent x dx, and then we're going to let u be secant of x. So when we take the derivative, we're going to get secant x tangent x dx. That takes care of that highlighted piece for us. And so we're going to get, all right, u squared minus 1 times u squared du. We'll distribute, and so we see we're going to get u to the 4th minus u squared. That's a funky u. Du. And then when we integrate this, we're going to get u to the 5th over 5 minus u to the 3rd over 3 plus some constant c. We know that we are dealing with secant, so we're going to go 1/5 secant to the 5th x minus 1/3 secant to the third x plus some constant c, and there is the solution for this one. Okay? The other way to attack this problem, and I'll wait for you guys just to make sure I'm not rushing you. Let me know when you guys are ready. All right, cool. So then from here, what I'm going to do is instead of going tangent and secant, I'm going to go with sine cubed x, cosine cubed x, cosine cubed x dx. I'm going to change that tangent to sine cubed over cosine cubed. Right? So then what that's going to give me is sine cubed x over cosine to the 6th x dx. And how should we attack this? What do you think?
Should we do the same thing and turn cosine to the power 6x and the secant to the power 6?
No. So in this case, for this problem, what we want to do is we want to do a u sub of cosine. So in this example here, u would be cosine of x. So then my du would be negative sine of x dx. And look what happens. So in order to break it up so that I do have the du be something successful, I'm going to get sine squared x over cosine to the 6th x times sine of x dx. You see that? So then when I go to the u's, before I go to the u's, I'm going to go 1 minus cosine squared x, right? Because we can use the identity, over cosine to the 6th power of x times sine of x dx. Well, sine x dx, we need a negative, right? So I'm going to put the negative in front, and I'm going to get 1 minus u squared over u to the 6th du. Are you in agreement with me?
Yes.
Okay. So then from here then we're going to get, we'll break it up and get the integral of 1 over u to the 6th. In fact, I'll write it as a negative power du plus the integral of u to the negative 4th du. Agreed?
Yeah.
Okay, so then when we do the integral of this, I'm going to have the negative out front. I'm going to have a negative 6 plus 1 over negative 6 plus 1 plus u to the negative 4th plus 1 over negative 4th plus 1 plus some constant c. That's going to give me a positive 1/5 u to the negative 5 minus 1/3 u to the negative 3 plus c. Now, we need to remember that we have cosine as our u, so we're going to get 1/5 cosine, and in fact, I'm going to write it in the denominator just to make my life easier. 1/5 cosine to the 5th power x minus 1/3 cosine cubed x plus c. And we could leave it here if we wanted, but we can also write it as 1/5 secant to the 5th x minus 1/3 secant to the 3rd of x plus c. And we get our same answer that we had before. So it's just showing you that there's different techniques. This one worked out to be the same answer. It doesn't always happen that way. But I'm just trying to show you some techniques so you guys can be successful. Different ways to do it, right? It's a bit of a trick. Okay, can I go on to the next problem?
Yeah.
All right, so in this example here, this is e to the square root of x. I know it doesn't show it very well, so really the way you should see it is e to the square root of x dx. Okay? A technique to attack a problem like this is we have a problem with that root there. So there's some manipulation that we could do in terms of ln's and whatnot, but instead of attacking it that way, I'm going to attack it by saying, hey, let u equal the square root of x, and then I don't want to deal with the roots, so I'm going to square and go u squared is equal to x. You agree with that, correct? That's still equivalent. It's just now saying that my square root, my x value has to be positive, but since it's square root of x, we know it'll be positive, right? There's a restriction there. So I'm going to get 2u du is equal to dx. So when I go to set this up, this problem is going to become 2u e to the u du is equal to e to the square root of x. Is there any questions on that? We're okay?
Yeah.
Okay. So then from here, if I pull out the constant, which we can, I'm going to get u times e to the u du. And what method do I need to use to be able to solve this integral? Takes practice, but you should see that since this is a product, this should be a UV substitution. Okay? It should be a UV substitution. In fact, may I change my U sub and call it an A? Can I call that an A? Are you guys okay with that? And the reason I want to do it is so that you don't have confusion when I do my UV sub. Okay? So when I do my UV sub, my U is going to be A. My dV is going to be e to the A, dA, right? So then when I do my derivative and integral, this is what I'm going to get, right? And so the integral for this thing tells us it's uv minus the integral of v du. So we can't forget the 2. So I'm going to go 2 times uv, so that's a, e to the a, minus the integral of v du. So that's going to be e to the a dA. Correct?
Yeah.
Now when I do this, I'm going to get 2a e to the a minus the integral of e to the a is e to the a itself. Let's not forget the 2 plus some constant c. If I multiply by 2, it doesn't matter. It's still just going to be a constant. And now what I need to do is do my original substitution, remembering that my a was square root of x. So I'm going to get 2 square root of x, e to the square root of x, minus 2 e to the square root of x plus c. Isn't that weird that e to the x is the integral, and yet the answer has e to the x in it? Strange. Just trying to show you guys some different techniques to solve these problems. Yeah, the tricks matter. Are we okay?
Yeah.
All right. Our next problem, we could do a ton of ways, right? We could try to do, all right, could we do a u sub of the that whole quantity and then do some convoluted derivatives? We could. I mean, it would get really, really, really complicated. So we need to think about how we want to attack this problem in the easiest way possible. When you see a problem like this, we want to see if we can break it up. And so the only way to be able to break it up is to make that numerator get out of the radical. And so to do that, what we need to do is multiply top and bottom by the numerator. Because when we multiply top and bottom by the numerator, what ends up happening is we get we get the radical to get canceled out, right? So we end up with something very cool. 1 minus x over, and then the denominator is a difference of squares, and I get this. Okay, but now since I have both numerator and denominator, one of the things that we can do is break this up into 2 integrals. So breaking it up into 2 integrals, I'm going to get 1 over the root of 1 minus x squared dx minus the integral of x over the square root of 1 minus x squared dx. And we end up with a lovely little problem, right? We could do trig subs, we could do u subs, we could do all kinds of things. For the first one, we could do a trig sub and do x is equal to 1 sine theta and go through a whole process there. But that's not the most efficient way to do it. There's an efficient way, and the efficient way is how I started the day. It's this guy right here. Because see how we end up with 1 over 1 minus x squared? We know that that's going to be sine inverse. And so knowing this table well to reference is going to save us time, as opposed to trying to do trig sub to this problem. There's some efficiency that we can use. So seeing that efficiency, we know that this is going to be sine inverse of x plus, to do the integral of this guy, here the method to do it would be to do a u sub, right? So our u, well, I'll just do the u sub. The u sub would be 1 minus x squared. And so I'm going to get du is equal to a negative 2x dx. I'll bring the negative 1/2 over to the du. And so I get x dx, which takes care of the numerator. And so what I end up with is a plus 1/2 integral of du over u to the 1/2. Agreed? Now when we go to do this integral, I'm going to get u inverse of x plus 1/2 the integral of u to the negative 1 power du sine inverse of x plus 1/2, and now I'm going to do the integral. It's a negative 1/2 plus 1 over a negative 1/2 plus 1 plus our indefinite, which is going to give us sine inverse of x plus the 1/2 and the 2 are going to cancel. If you don't see that, please feel free to ask. U to the 1/2 plus c. But I know what u is, so I'm going to get sine inverse of x plus the root of 1 minus x squared plus c. And that is our solution. Is there anyone that doesn't see the example on how I get rid of the 1/2 there? Meaning right here, how this, the fraction, the coefficient gets eliminated, becomes a 1. Does anyone need me to show it?
I think I get it, but I just want to be clear. So what happened was, so in the denominator, the negative 1/2 plus 1 became 1/2. And then on top, the exponent became 1/2 as well. So the 1/2 just canceled out with the denominator, which gave us that u to the power 1/2, right?
That's it, yeah. Yeah, because when you have a fraction in the denominator, it's multiplied by the reciprocal. That becomes a 2, and the 1/2 times the 2 become a 1. So that's all I have in terms of lecture for today, because this work is a big lift, right? So, and like I said, I gave you guys quite a bit of homework, because really the best way for you to get good at these integrals is to go and suffer. So I also gave you a week on this homework, so this homework assignment won't be due till next Monday. But like I said, I gave you 40 of them. So there's some work to do. And it becomes so important to know all these techniques. If you're going to be an engineering or a math major, this section is going to be huge in terms of being able to know how to do and solve integrals. So this is putting a lot of tools in your shed, okay? So you're going to pay the piper, but you're going to be better for it, okay? And I'll answer questions next time we meet, but that's all I got for today. Do you have questions for me in terms of homework?
For 7.4, I requested an extension.
Oh, I think I granted all those. Let me check. Let me just confirm. I think I did those all today. Have you checked today?
I checked a little, well, like earlier, but nothing was.
Okay, let me just confirm.
Yeah, only 7.5 pops up.
I just heard one person quietly. Okay, I see it. It's funny, I thought I had done all these today, but okay. Now I gotta move these chat things so I can do it. So many things in my way. Okay, there's one. And let me do Brian's. Yeah. All right, that should be there for you. Okay. Besides that, is there any homework questions or anything you'd like me to work on, or do you guys just want to go try and attack this work and load me up with questions on Wednesday? Which is totally fine. We've only got 2 more sections to do, and we're done with this chapter. So on Wednesday, I'll do 7, 8. I believe it's 7, 8, and 7, 9, and then we're done. Let me see. Oh, 7, 7, and 7, 8, and then that section's done. So we're almost ready for our next exam. All right, I'm gonna stop recording.